log 1 over P of xn, which is equal to h of x super n, and we've achieved the entropy. Again, where I have to be careful when I actually investigate this precisely. But so this is the rough outline of why it's true. By the way, how large is P of xn going to be? If it's an ergodic process, it will be of size 2 to the minus nh, where h is the entropy rate, in which case you get compression to the entropy rate limit. All right, this is very useful. We already have the following. If x is a stochastic process, we just encode f of x, the CDF of f, into a sequence u. U will be Bernoulli a half. How many bits of u do we need to recover a sequence of n x's? Answer, essentially h of xn. X super n. Bits will suffice. So we're getting compression to the data compression limit, and we're doing it by this method. Is the method easy to implement? Yes, because you can do it sequentially. In fact, I can write an expression for f of x, at least in the Bernoulli case. F of x is summation of, all right, 2 to the something x sub I. That is, I either include this term of p's and q's or I don't, accordingly, as there's a 1 or a 0 there. And I've done it here out to length 3, and so on. Now, suppose we don't know P of xn for all xn and all n. In other words, we don't know the marginals of the stochastic process. We didn't for English text. Instead, we use P hat of xn, which we write this way. Product P hat of xi, given the previous things from I equals 1 to n. It's just writing the probability as the product of the conditional probabilities. This smart human or a computer estimates it. For example, here's a picture of the Mona Lisa. And we've seen this so far, and we ask you, what's this? So we have a raster scan across the Mona Lisa, which consists of ones and zeros. And now you want to estimate whether this pixel is black or white. Well, a good way to do it is to run a window, say, of length 7 across this. See how many times you've seen this one and whether it's, take the subset of times you've seen this preceding sequence of length 7 and then see what followed it up here. We're assuming essentially that the Mona Lisa is stationary. Well, it's a bad assumption, but it's an assumption. And then you use the empirical frequency of what you've seen to make your estimate here. And to keep you from betting all of your money, as we did last time, I'll buffer it and just say that even if you've seen that preceding sequence 20 times and it's always been followed by a 1, I will say that you've seen it 22 times. 1 extra time followed by a 0 and 1 extra time followed by a 1. In other words, the empirical probability will have at least a floor of 1 over n on what comes next, where n is the length of the preceding sequence you're basing your estimate on. All right. We use p hat to encode and use p hat to decode. In other words, we use arithmetic coding as if p hat is true. We calculate f hat, we do all of that sort of thing. Then, then we have if p hat is the estimate, est period, then xn maps into u1, u2 through uk, this Bernoulli sequence, where k is roughly log 1 over p hat of xn. Because we're using p hat as our compression and decompression scheme, so we have n bits goes to k bits, which is roughly log 1 over p hat of xn. So it's random, k is random. And the expected value of k with respect to the true distribution is p of x super n log 1 over p hat of x super n. Okay? So you've got data compression if p hat is true, but the true distribution is p, and this is over xn. But look, this is the same as summation p log, p log p over p hat times 1 over p. which is the distance between P of x super n and P hat of x super n plus h of P of x super n. But this, of course, is what we've been calling the entropy of the random sequence, x super n. And so this is the penalty. It's the wrong distribution. But the wrong distribution didn't cost us much. And if p hat equals p, if we're right, we pay nothing extra and we get the data compression entropy limit. So this is on the fly. So you want to compress images? Come up with a predictor based on empirical evidence or Fourier transforms or wavelets or whatever you want. Come up with any predictor you want. That's your p hat. Encode and decode as if p hat is true. Then you will achieve the entropy limit plus how far your predictor is from the true distribution. And that's all there is to it. You want to see what predictor is best? Just look at the data compression that results. You're essentially estimating this term. The people who gambled on